All right, everyone, it's time to start. So the first session after the keynote, welcome everyone. And without further ado, today we're going to talk about a slightly different way of designing your systems. And the reason that the basic idea of this talk is not to change everything you did so far, but I want you to look at from a slightly different perspective at the systems you're designing with. So if you need a too long, didn't read version of it, we're going to be talking about distributed systems and event sourcing, but from a different perspective. So first of all, let's talk about the monolith. It's something we are all familiar with. It's this huge, gigantic, it's not even an application, it's just a pile of code. It's this great thing that does everything in our company. I mean, who doesn't have a monolith in their current company? Like this huge application that does front-end, back-end, back office, generating invoices, reporting, pretty much everything. I mean, every single company has some sort of it. I'm working in a company like that. My previous company had a monolith, and my company before my previous company had a monolith like that. And this is what pays our bills. This is this big legacy piece of software that lies in the very middle of the organization. And we don't want it. There are these new trends of having services and what have you, but this is the state of the art. But hello, we want to change something. So what do? We want to split the monolith. And if you didn't live under a rock for the last couple of years, you know that everyone wants to split their monolith into microservices. That's the trend these days. And look what happens. So you have your monolith, you want to split it, and this is not actually a new idea. So someone, and I'll give you a guess here, someone said that all teams will henceforth expose their data and functionality through service interfaces. And it's supposed to be HTTP, core, but whatever. All teams should expose services and interfaces. Do you know who said it and when? It was Jeff Bezos 15 years ago. In 2002, Jeff Bezos, the CEO, not even a CTO, CEO of Amazon, said it, that all teams are supposed to use service interfaces. And this was part of his memo that leaked. And this memo was ended with this quote: anyone who doesn't do this will be fired. So he's kind of a nice guy. And so he did. He basically enforced everyone at Amazon to build their systems on top of services, and services that are communicating with each other. That's great. And by the way, I'm going to leave you a link to the slides at the very end. So this is the Amazon architecture a couple of years after this memorable memo. Or, sorry, actually, this is an Ebola virus. The architecture of Amazon was even worse. This is the real picture. It shows different services communicating with each other. I'm not saying it was a mess. I'm just saying there were many services intercommunicating with each other. And I wouldn't say that this was a perfect architecture. Definitely, there were service interfaces. Definitely, services were communicating with each other. But this wasn't something beautiful. So, hey, Steve Yege, he was working for several years at Amazon, and then he was working for several years at Google. He once wrote another memo, another internal memo, comparing the way Amazon builds software and Google builds software. So he was trying to convince the Google CEOs and other people that Amazon is doing something good, Google is doing something good. How can we kind of enrich what we're doing at Google? And once again, this was supposed to be an internal memo. However, he published it on Google+. He misclicked something, and rather than publishing it to Google employees, he published it to the whole world. So that's how we know it. So Steve Yege said that Amazon's code base is a disaster with no engineering standards whatsoever. And by the way, this is the state of the art in 2011. So it doesn't have to be this way. It's not about bashing Amazon. This was the state of the art quite a few years ago. So that's what he wrote. But he wrote quite a few interesting observations what was happening at Amazon these days after this CEO's memo. So pager escalation gets way harder. So guess what? We have services. We no longer have one huge application where when something fails, you have one very long stack trace, and you can tell by the stack trace what's going on in the system. Now you have multiple services, and you have to track down what these services are doing, which services are calling each other, and trying to figure out who is actually responsible gets really, really hard. And this is especially hard when teams aren't mature enough, because that's the whole point of having separate services, that each service is governed by a different team. And suddenly, it's just a play of ping pong. You're trying to figure out which team is supposed to handle this particular failure, especially in a distributed system where one failure causes another, and another, and another, and they are just cascading into the whole ecosystem. And that's a really bad thing. So pager escalation gets way harder. That's the observation that he made like 6 years ago. It's not a new knowledge. But that's just the beginning. So very serious quotas and throttling in every single service. You know what? When you have a distributed system, every single service that misbehaves or it's coded improperly can actually become a distributed denial of service attack source. Your service can bring down 3 other services, and 3 other services can bring down 9, 27, whatever. And suddenly, half of your production doesn't work because one tiny service makes too many HTTP requests. This can happen. What's more, monitoring and QA are the same thing. So guess what? Testing such a complex system becomes really, really hard. So rather than testing everything extensively, having very, very expensive testing environments, you just go to production and have a lot of metrics, a lot of monitoring, a lot of end-to-end tests that are running on the production or semi-production system. And this, of course, brings much more risk into the whole process. And that's not the end. Service discovery mechanism. This is something they discovered, the service discovery mechanism, quite a few years ago, that having so many services, you actually need some way of registering and looking up these services. And come again, this is several years ago. This is not new knowledge that just like surfaced with microservices. They already knew it a decade ago. And debugging problems from someone else's code, especially in a polyglot environment where every service is written in a different language, different platform, different database, different server, this is becoming really, really hard. And how are you supposed to figure out which team is responsible for a given failure if the service you're troubleshooting is written in Clojure, or in Node.js, or maybe in God knows which language, which happens to be the best one to fit this particular use case? So all these observations made a decade ago, and suddenly this monolith doesn't look that bad after all. But you know what? Even though these developers were kind of threatened to get fired, even though they came across so many issues, they still went through the service architecture. And by the way, the premise of this memo by Steve Yege, the one that leaked because he accidentally clicked sharing button, the premise of this memo was that they actually enjoyed it. So having all these services communicating with each other was actually beneficial despite all the issues they run across. And despite all the issues that we are rediscovering, like service discovery, these days. So okay, we kind of settled on the fact that we still want to have services rather than a monolith. So what do we do? Well, the easiest way to do splitting of a big application is to kind of discover which parts of the application can be split back, and then have some really well-defined set of interfaces. And these interfaces previously were just normal Java calls. So you have one class that calls another Java class through an interface, or maybe not. And now you turn this interface into a RESTful interface, or any other protocol, but RESTful over HTTP happens to be the most well-known. So this is actually a nice approach. So you define so-called bounded contexts. If you are a domain-driven design geek, you split your application, you have a well-defined anti-corruption layers, and so on and so forth. The biggest thing here is that rather than having an ordinary Java call, you now have a remote Java call. But the rest of your application just works, right? It used to be calling a Java code, and it's still calling something that looks like Java. So here's an example. You call a standard Java thingy. Doesn't matter what it's doing. Imagine it's doing some database transactions, some computation, whatever. This is very cheap, and this is very safe, despite, I don't know, Stack Overflow error. By the way, Stack Overflow, it's not just a website. It's also an error in JVM. So apart from a Stack Overflow error, nothing bad can happen here. And JVM will most likely inline this invocation, so you basically pay no price for invoking it. And then we turn into services. So we turn this into a service because we somehow thought that having triple as a service is a good thing. So we turn it into a service, and there are many, many tools that can do it. This is, for example, Feign, which is on its own a very nice tool. You just take a Java interface, you sprinkle a bit of annotations, and voila, you have a service. So it generates a proxy. When you call this interface, it automatically makes a RESTful call. And you know what? It still compiles. Because you had code that was relying on an interface, and it still relies on an interface. So no problem. But what we often forget is that there are so many layers of abstraction that we are hiding. So guess what? When you're making a RESTful call, even if it's hidden behind all these nice frameworks and libraries that are wrapping it, you still have like 10 or 20 different failure modes that can occur. You might not have a connection to the network. The thing you're trying to connect to might not exist. It might not be listening on a given port. It might be listening on that port, but not returning anything. It might be returning something, but not a number, but JSON or a string or whatever. So there are issues with encoding. And the worst failure scenario of it all, you are connecting to someone, and you just don't get anything in return. You just have infinite latency. You're calling a service, and then you never get a packet back. Because people forget that there's TCP/IP protocol underneath, and you're exchanging messages between two servers. So there are so many different ways in which this tiny little code can fail compared to our ordinary Java interface. And don't forget that since we are crossing threads and we are crossing JVMs, we are crossing servers, you actually lose transaction consistency, you lose tracing and all this stuff. And you no longer have nice stack traces because it crossed the boundary of machine. So there are so many issues with it. And these issues were actually discovered many, many years ago, and I'm pretty sure you know the fallacies of distributed computing. And I'm going to go very, very quickly through them from the perspective of what we already saw. So first fallacy is that the network is reliable. And if it was reliable, we wouldn't need tools like Hystrix. Hystrix is a great tool. It encapsulates all your remote calls, all your distributed calls, and tries to put a circuit breaker on top of them. So that when your system goes down, or when one of your dependencies goes down, you are not bringing down the whole infrastructure. And that's a wonderful thing. It kind of solves the problem that we introduced ourselves by having a remote procedure calls. RESTful, Corba, gRPC, Avro, whatever. It's still a remote invocation of a remote system with all the issues I already mentioned. So this is the first fallacy. Now latency is 0. Yet another wonderful tool, it's called Zipkin, and there are many others like that, that allows you to implement distributed tracing. So distributed tracing is basically like a profiler on the service layer. You know which service took how much time during the invocation. So you can see, for example, that you are calling some services too many times, or one of the services is too slow, so on and so forth. So another latency, bandwidth is infinite. Very, very rarely we are hitting the limit of memory or CPU when doing normal enterprise development. However, hitting the bandwidth limit is actually possible and very often overlooked. So we invented batching, we invented compression and all these mechanisms just to spare a little bit of the internet traffic, of the network traffic. So the network is secure. I mean, if you're doing services, there are two ways of implementing security. Either not implementing security, so everything is just wide open, or having all these governed SSL certificates, OAuth, authorities, and so on and so forth. Both of these are kind of extreme, but you have to think about it. You don't think about security when you're calling one Java class from the other, or not to that point. And that's something that was literally mentioned by Steve Yege. There is just one administrator, which is not true. It's a fallacy. Every single service has a different administrator, and very often the actual administrator will not admit that the failure is on their side. They would claim that it's just another service that malfunctions, and you just have to go from one node to another, trying to find the actual person who can fix it. And what used to be minutes now turns into hours. And the transport cost is 0. I love this quote, the internet is running in debug mode. Do you know what it means, what the Rüdiger Müller was referring to? Come again? Once again? Yes, text protocols, yes, sorry. So text protocols, XML, JSON, HTTP prior to 2, because HTTP 2 protocol is now binary, which saves us a lot of bandwidth. So once again, we had to invent a new version of HTTP protocol just to avoid the problem of encoding and transport cost. So many issues have come to life just because we started with distributed architecture. But once again, Amazon guys didn't really think it's that bad, and I'm not claiming that you should not go through distributed services. I just want you to know what are the consequences. And knowing all these consequences, let's start with the actual talk. I would like to show you something which I called a Hollywood principle, but on the architectural level. I guess you, like, at least most of you know what the Hollywood principle is, right? It's about calling. I'm not calling you, you are calling me. So the Hollywood principle on the architectural level is about not collecting the data you need, but having this data when it's needed. And I'm going to very briefly, in a second, show you what it means. So this is a well-designed service architecture. It somehow mimics an application that tries to make a bid on a stock market. So on the left side, you see a bidding component. And the bidding component is supposed to do some, well, bidding, so buying some stock. And in order to do so, it has to contact 3 different services. One to figure out what is the price of, let's say, IBM. Another to know what's the current portfolio. So it has to know what do we own currently in order to make a purchase. And it also has to calculate risk for some reason. And in the very end, it makes a post request just to make an actual quote. Do you think it's a good architecture from the service perspective? Some people are nodding their heads, some people are saying, nah, not really. So it is sort of well structured because we have different services that are doing different things. That's a good thing. Definitely there is a single responsibility principle. Every single block has one responsibility, and I guess they're doing it more or less independently. We have RESTful calls here, and it seems like a modern service architecture because it's not using SOAP, it's using REST. So it has to be modern, and probably JSON underneath. So this is our architecture, but there's one big issue with it. Everything is synchronous. This means when the component on the left, the bidding component, and probably the bidding component is not the director, it's probably just a downstream of yet another dependency. So imagine this graph goes all the way to the left, and maybe there are some other dependencies all the way to the right. It's just a fraction of what we see here. So imagine when a bidding component wants to make a transaction, it has to go to the prices component and get a response back. It has to go to the portfolio component and get a response back. And it has to go to the risk component and then get the response back. You notice I was doing these really long pauses when I was telling the sentence, and that's not a coincidence because every single dependency introduces latency, which means that the latency of the bidding component is the total latency of all the components it was invoking. And just to be clear, the fact that you're using some fancy asynchronous framework, for example, RxJava or Completable Future or Akka for making synchronous HTTP requests and responses, doesn't mean you're having an asynchronous architecture. You're just using a library that has thread pool underneath, but you're still waiting for a response. So in order to proceed, you still need to make a request and wait for a response. There is not a chance of completing the bidding transaction without getting a response from every single dependency. And if you make them concurrent, it makes things a little bit better, but you still have an issue with fault tolerance. So when one service goes down, everything else goes down. So when a prices component, portfolio component, risk component goes down, everything doesn't work whatsoever. All right, so what can we do about it? Well, I was listening to this podcast one day, and Scott Belwer, a really prolific guy, I think, in the Ruby community, said that you cannot query data from a service. And this is the golden rule of service design. I mean, what the heck? What does he mean you cannot query data from a service? I thought that's the very basic idea of having a service architecture. You have services, and one service queries data from another service, gets the data back, and do something with the data. and then it queries the data from another service, gets the data, and does something with that. That is fairly obvious. So how are you supposed to design your systems? This can somewhat be translated into object-oriented programming. You're supposed to tell your objects to do something rather than ask objects for data and do something with this data. So he's kind of not violating the basic rules of object-oriented programming, but on the architectural level. So what do you do about it? How can you live without querying data? After all, we do want to have a user service, we want to have an account service, we want to have a purchase service, and all of these are basically just glorified databases with RESTful interfaces. So you have a database, you have RESTful interface, and you have CRUD on top of it. That's our services, nothing more. And the services just keep calling each other, querying data from each other. And that's not a surprise that when one service goes down, all the others can't work because they don't have necessary data. So what can we do? Well, the basic idea is to publish the changes rather than expose the data via interfaces. So how does it work? Imagine we invert the arrows. And when you're an enterprise architect, this is really simple. It's just one click in your IDE. Rather than getting data from services, imagine that it's the services that are giving you the data kind of eagerly. So this is the prices component. I'm no longer asking the prices component, what's the price of IBM? Instead, I am passively subscribing to changes from this component, and this component will just start streaming the data to me without my, well, with my permission, but without my request. So every time the price of IBM changes, I'm going to get a message in some format. It can be a message queue, it can be JSON, it can be WebSocket, whatever. I'm going to get a message saying the price of IBM just changed. And the same applies to my portfolio. Every time something happens to my portfolio because I bought something or I sold something, I'm going to get a message from this component. I subscribe to these messages because I somehow said I'm interested in the data from that service. So it's going to start pushing the data to my service. Do I need the information that the price of IBM has changed? Not at the moment. But I will keep it locally in the bidding component. Inside the bidding component, I'm going to build a denormalized, very specific database, denormalized to my specific use case. And what's the easiest database I can think of? Well, it can be a concurrent hash map, if there is not that much data. Or it can be a key value store, or it can be a file, whatever. The thing is that rather than having an external service and an external database, it's still a service. Rather than having an external service that knows the data I need, I have all the data in myself. So whenever a request to bid for some stock comes to my service, to the bidding component, I don't have to look up this data in a different component because I already have all the data in my local store. I am totally independent. And that's a good thing, because even if the prices component goes down for a few seconds, I'm still up. I can still work because I have all the data. And to make it even more interesting, I know how old or how fresh the data is, because I know when was the last time I received an update. This leads to eventual consistency, but we will talk about it later on. All right, and the same applies to portfolio, whatever. This doesn't apply, notice, this doesn't apply to a risk component, because the risk component is a typical computation thingy. So it makes no sense to publish the changes about risk because it's just a calculator, it's a stateless calculator. So that's why the title of the talk, asynchronous by default, synchronous when necessary, or when it makes sense. So that's the basic premise of the architecture. Everything clear so far? All right, we'll have some time for the questions toward the end, because I'm pretty sure you have some. All right, so this is our architecture, and it seems really cool. At least it has some advantages. The advantages are that even if the components on the right, at least some of them, are down, our component still pretends to be working. Maybe with some stale data, but at least it seems to be functioning. So we are not bringing down the whole system. And another advantage is that The only latency we have here is the latency of the bidding component. We no longer make a request response invocation to different services because we have the data in our local repository, whatever its implementation is. All right, so what else? We got rid of the problem that we have to call one service into another, so we no longer have to make an HTTP request or gRPC or whatever into a different service. However, there's still some sort of a temporal coupling. So this is the biggest problem when you're making a request response. When two systems are communicating with each other using a normal request response protocol like HTTP, both of these systems have to be alive in order to proceed. When one of the systems, when the client is down, then there's no one to call. When the server is down, then client has no one to call. Both of the systems have to be alive at the same time. We can have some load balancing, we can have some blue-green deployments, we can have some fallbacks and so on and so forth. And by the way, if you know Hystrix, there's a lot about fallbacks. And the fallback is that when one system doesn't work, so you're making an HTTP request to a system, and the system doesn't work, in the documentation of Hystrix, there's a lot about fallbacks. And the fallback is like a backup procedure. So what to do when the real system doesn't work. And their grand example is that you are asking, for example, a recommendation engine, and the recommendation engine is down. So rather than showing you your personalized recommendations, I'm going to show you bestsellers, which is something I have already. This is my fallback. However, more often than not, you do not have a sensible fallback. Because when you need to know what's the current balance, or what's the current portfolio, or what's the current price, there's no fallback. You cannot say that, I don't know what's the price of IBM, so let's say it's 100. There's just no such thing. If you have data inside of your local store, because you were listening to the changes, you know that the last known price of IBM was $100.25. And this price is 7 seconds old. Can you live with that? It's your business decision. And by the way, you always have stale data, because when you ask a component and you get a response back, then this data can probably already be stale. You just have no idea. But coming back to temporal coupling, so making a request-response communication is not such a good thing. But there's yet another thing. So you still need this wire connection between two services, because you are subscribing to changes directly. Remember, I was making direct connection between bidding components and prices and portfolio. This direct connection was subscribing to the changes using WebSocket or TCP or IMQP, whatever. So what if we introduce another layer of abstraction, because this always works. And this extra layer of abstraction would be something that I would call an event database, or a journal, or an event store, whatever. It's this tiny component. Actually, it's a big database in the very heart of your system. And this big database is going to store every single important event that happened through the life cycle of your system. So I'm talking here about price changes, of portfolio changes, of user accessing some data. Everything important that happened in your system is going to go there. This is basically an audit log of everything that happened. And many people ask, okay, so how can you actually implement it? So first of all, there are products that can do it. There are message brokers, there are message stores like Kafka, for example, but this is a different story. And also, many people are asking, so how are you supposed to store all this data? It's going to just grow infinitely. But guess what? This is already a requirement in so many different areas. You always have to have an audit log of everything that happened to your system. It's just that it's always like an afterthought. It's another requirement. I'm telling you that this should be at the very heart of your system. When something interesting happens in your architecture, you are putting it into your event database. When you want to know what happened in the system, like when you want to know what's the current price, you just subscribe to this event database. You start draining the price changed events, and you know what's the current price. So that's how it works. Notice that risk component is still a separate service, and making the actual bidding is still a separate service, because it basically makes no sense in this case. And guess what? There are some other benefits. Remember on the previous picture, we were asking about portfolio at a given date. So here you have get portfolio at 25th of January 2017. And when you want to design such a feature in normal system, you actually have to, well, design it as an afterthought. So you need some sort of history table or something. However, with this type of approach, you get it for free. So what do you do when you want to know what's the current price? Well, you just listen to the price changed events, and you know what's the current price once you go to the very end. But what if you need to know what was the price on 25th of January? Well, you do basically the same thing. So you start listening to these events over and over and over and over. And when you reach 25th of January, you stop. And what happens? Your system is now at the state of 25th of January, which means you know what was the price on 25th of January. And it brings all sorts of other interesting features. For example, when there's a bug on production, well, when there was a bug on production 7 months ago, you can take all your events from the production, you can replay them on your local developer machine, and you can debug your system as it was behaving 7 months ago. You have a complete database from 7 months ago. And actually, some databases have this feature built in. For example, Oracle, I believe, with their Wayback or whatever it's called. So that's yet another thing. So we have audit data. Do you know this application? Yeah, it's Trello, but I can give you quite a few other examples. It's Google Docs, Pocket, Evernote, Endomondo, and many, many others. What they share in common is that they all work reasonably well offline. If you design such an application that works typically on a mobile device or something that doesn't have a constant internet connection, you have to think about the state where you don't have network, or when the network just goes up and down all the time. How naively implemented application will work? Well, it will just say that I don't have internet connection, I will not show you any data. If you're a little bit more clever, you will actually cache the current state so that when you open an application, at least you know what was the last state. But you know what? With Trello, and many other applications like that, not pitching for Trello in particular, in Trello you can actually make modifications to the state on your mobile device even without internet connection, and it just works. I mean, you don't see these modifications on other devices, but at least the application doesn't crash. And by the way, you can make modifications on other devices which are also not connected to the internet, and it will somehow figure things out. And I wasn't implementing Trello, but if I would do it, I would go for the exact same architecture. So every single change that is made on the board, so moving these cards, adding comments, removing them, and so on and so forth, is stored as an event. So rather than modifying some mutable data structure, I'm just holding an event. I moved a card from this column to this one. I added a comment, and so on and so forth. And when the internet connection goes back, I simply flush all the data. I have a queue of pending events, and vice versa. I take all the events that happened when I was offline. And do you know a system that works this way? Pushing and exactly, Git works this way. And there are so many other examples of systems that are working this way. Not only Git, of storing change sets and exchanging these change sets when the systems are finally back up. It seems like it's just a reasonable thing to do. It's a reasonable thing to do. It's used in blockchain. I mean, there is no single presentation on a tech conference that does not mention blockchain, so I had to do it as well. So blockchain is basically just a distributed journal of events that's shared by all the parties, an immutable, ever-growing journal of events. But that's not everything. You have banking. So how is banking implemented? Transferring money. So if you're a hipster, you are implementing bank as a MongoDB database. And the first thing you have to understand when using MongoDB is that it's not transactional. It's transactional on the level of a single document. And there was actually a, I don't know, it was Bitcoin exchange or something like that. What was the name of it? Flexcoin. So I guess it was Bitcoin related. So they were using MongoDB to implement transfers, and because they didn't understand transactions, they actually allowed people to transfer the same money from one account to thousands of other accounts. And this is like a school type of example when to use transactions. So how would you implement transactions? knowing that MongoDB doesn't support them to the level you want? Well, you would go with relational database because they clearly didn't have any audit data. They were just mutating state, so they had no clue. Everything was mutable, and there were race conditions. So you can imagine there was if somewhere, like if this account has some amount of money, take this money here and put some money there. But actually, if there are multiple threads interleaving, you can actually transfer the same money into multiple places. So what can you do? When you learned SQL in your university, this is kind of the university type of example of transactions. You open up a transaction, you select the current amount on one account, and within one transaction, you are transferring money from one to the other. No bank on earth works this way, unless you are making a transfer between two accounts in the same bank. No one works this way. And do you know what happens in the real world? There is something called Swift, which is a protocol for exchanging messages. They have an audit log, and they have a very reliable message broker that allows banks to transfer messages between each other. And that's why in banking you have eventual consistency. And this eventual consistency means, where is my money? You are transferring money to someone, and this money disappears from your account, and it's not on the target account. This is the eventual consistency that happens for years in the banking industry, and no one collapsed. It just works this way because they have full audit log. And even if you have an overdraft, they know. They're going to catch you, and they're going to take your money. Nothing's going to be forgotten, contrary to the MongoDB example. And this is the basic principle. Like, they're just sending messages. Please transfer this amount of money to this account, and that's it. But that's not it. So this also happens on the front-end side, and it turns out that our front-end colleagues discovered the power of state changes, immutable state, and transferring from one state to the other quite some time ago. So the Atwood's law, I'm pretty sure you know it. Actually, someone believes that, I'm just going to leave it up to you. So it seems like the front-end guys already discovered the power of keeping the state as a sequence, or maintaining the state as a sequence of events. So what happens? There's, for example, Redux, a very, very popular library, a tiny library that you typically use on top of React. And guess what? In Redux, all you do is that you're always modifying a global state via messages. So there's no mutating of current state. There is no one blob with state. There's an immutable state, and you modify it by applying events on top of it. And the whole idea of Redux is that you can apply the same events on the client side and on the server side. So this makes it very easy to keep the same state on both ends, and also to have offline applications. This is precisely what we were talking about before. All right, so going back down to earth, there are quite a few implementations of an event store. I already mentioned Kafka. There is Get Event Store from Greg Young, Event Store JS, because everything's better with .js. I just learned yesterday that Axon Framework has their own implementation of an event store as well. This is something that's really common in the industry. You just have to learn to realize it. The whole banking industry works this way, and they somehow survived. But just because they survived, we have to talk a little bit about caveats. So I mentioned already what about eventual consistency, and I don't have a good answer for it. The good answer is that you just have to deal with it. You just have to survive with this fact, and you just have to remember that eventual consistency is the fact of nature. That's it. However, there are a few things that you can do. For example, you can embrace eventual consistency at the user interface level. So rather than claiming that everything is instantaneous, you're just saying to your user, okay, this is going to be processed within some time. There are even weird techniques, but some people are claiming they work, that when you're making a request, you are actually you are actively waiting for the event to get applied. So you're making some requests, and then you are waiting for this event to get published with in your event store, and then you are showing your user interface. And people are claiming that it takes like 100, 200 milliseconds, so it's not perceivable by users. But that's one thing, and the other thing is just like try to think as an ordinary user. And as an ordinary user, you know that things aren't instantaneous all the time. But this is something you have to deal with, and you have to understand that when you're making a bid, the portfolio component, coming back to our example, the portfolio component might have stale data. At least you know how stale it is, because you got the events, and you know when was the last time you got the event. But that's the fact of nature, so we have to somehow deal with it. So what else? When you're starting up a new service, this is a huge advantage, but also a huge cost. When you're starting a new service, and you want to know what's the current portfolio, or you want to know how the price of IBM was changing over time, this does not require any extra implementation on your side. You just start subscribing to the portfolio changed event, or sorry, price changed event, and you just keep listening, and you finally come up with the price. The problem is that it takes time. And if your system lives forever, like 5, 10 years, then you would actually get a lot of events to process. And there are some interesting techniques to overcome it. For example, you can have snapshots. And a snapshot is like this special capture of the state that happens periodically, once every 1,000 events, once every day, once every something. And when you want to know what was the price like 7 months ago, rather than rebuilding everything starting from 2000 to 7 months ago, you just take the last known snapshot and rebuild events from that snapshot. So you can have like a special procedure that builds these snapshots. So this is basically a denormalization thing to do. But on the other hand, the fact that you have all the history stored as a first-class citizen makes it really, really easy to build really interesting, for example, monitoring or reporting tools. And having all the events actually allows you to build applications that you didn't anticipate, and you simply forgot to store a given piece of data. It's very often that a business comes in and wants to know, like, what was the average basket size throughout the last 12 months after 15 minutes since login? And you just have no idea because you never stored this data. Maybe you stored it in Kibana and you're then parsing your logs, but that's all you got. When everything is stored as a first-class citizen in your event store, then you can easily implement features that you haven't anticipated previously. But still, it's a cost. And I want to leave you with a kind of a philosophical question. Can World Wide Web work this way? And by this way, I mean publishing changes as opposed to making requests and responses. And actually, I'm pretty sure you all know it won't work this way. And this is also a thing I want to leave you with. So what I've shown you is type of an architecture that can help you in some use cases. It's not a good fit for all the use cases. It won't work in many areas. But what I want to leave you with after this presentation is that when you're designing a new system, think about communication protocols. Think about how you communicate with each other. Do you really need a request response, which gives you this very tight coupling, a temporal coupling, a physical coupling between services? Or maybe you can lose this coupling a little bit just to make the systems more reliable and more fault tolerant. So I'm leaving you with this, and these are the slides. Maybe there are some questions, so feel free. Yes? How do I deal with what? Sorry? Mm-hmm. Yeah, so there are some techniques. So first of all, there is a book by Greg Young called Versioning in Event Distributed Systems, in Event Source Systems, something like that. So there's like a whole book devoted on how do you deal with this thing. One thing you can do is that when the change is not trivial, you can actually reprocess all the events and reformat them into this new schema. And this way, everything works up to date. I'm going to spare you with normal advices, like just keep your events backward compatible because the system changes. Another way is to basically just publish to another topic or publish another type of events. So old systems still consume old events, and new systems can start consuming new events. And then you get the transition period. And you can also retrofit the old events. And I didn't first catch your question, but there can be another question: what to do with large binary files. So how do you deal in such systems? And in this case, you very rarely store the actual binaries in your events. More often, you will actually store them in some external storage, S3 database, whatever, and then you just put a URI in your event. So that's kind of goes away from this architecture because you have some external storage. And the whole point of this architecture is that you can rebuild your production barely from an event database. So that's the only thing you need in order to get back online. But when you have a very large blobs, you still want to hold them in a different storage. So does this answer your question? Okay, thank you. Yep. Yeah, here you go. Okay, so the question is about stateless services that were actually down at the moment. So this architecture doesn't really solve the problem of stateless services that actually you have to call. I mean, this was an example with risk service, right? The question was what to do when the risk service is down. You do need a risk service because there's no way of making it offline or event sourced or whatever. So I'm not saying everything should be built in this way. If you want to somehow make stateless services or services like risk more fault tolerant, you have standard ways of load balancing, different data centers, fallbacks, and so on and so forth. But this type of architecture doesn't solve it. It solves a problem of taking data from one thing, from one service, and then restoring it, but not stateless services. Okay? We have time for one more question? I think so, yeah? Okay, so I guess it's the last question. So that was a very good question. What happens with the bidding service when it starts up for the first time, the database is empty, and it wants to process, for example, an IBM transaction, but it doesn't have any IBM event so far, right? That was the question. Or an even more complicated situation, it does have a price of IBM, but the price of IBM is, for example, 3 months old, because we already got it, but it's really, really stale. So when it doesn't have any events about IBM, we do have to think about it. It's a situation that can happen. You might want to fall back into a normal request-response architecture in this case, because you don't have the data. I would say that this is not a very typical situation that you didn't get any event about a given aggregate route, but it's possible. So in this case, you might want to say, I don't have price for IBM, and this is a very abnormal situation, and I'm returning 503. I have no idea what's going on. You can fall back into making a request response to someone, or you can wait a little bit more, because most likely the event will come up sooner or later. It all depends on how your system is built. So you can either have fallback, or you can just say, I have no idea what's the price of IBM, or you can fall back into an old price that is a couple of months old. Maybe it works for you, maybe not. Right? Okay. I guess that's it for the questions, so thank you very much. Hope you enjoyed it. Have a good day.